curve. So, we can say that first curve, one part, that convex part is the basically the liquidus temperature, and concave part is basically the solidus temperature. That means, within this there is a change of the phase from the, it starts from the liquid phase and then comes to the solid phase. But here there are two components are there. So, this is a specific alloy system. So, in this case, if we look into at point A is a single point. So, that single point actually indicates the melting point of the component A. So, that means of the component A means here it indicates that it is a pure metal. So, on this pure metal it follows the simply cooling curve like that at this point if it is a 100% composition of the single component, then here if you see that the phase change happens over a range, phase change happens one constant temperature, and then after which it after cooling it comes to the ambient temperature. But similarly, if you look into the point B also, here we can see that at point B it is also pure metal, but the different metal. So, here the melting point are different as compared to the metal A. So, here also you can see that phase change also happens over a range of the time, but at constant temperature. So, it follows the similar kind of the cooling curve like the pure metal A. Now, if the alloy system consists of the material A and B, it is a mixing of this thing. So, it becomes alloy. So, in this case the phase change starts at point at this point. So, that actually exactly on the liquidus line. So, here at this point it just starts from the changes of the phase from liquid phase to the solid phase. So, the change of the phase happens over a range of temperature, and here correspond to this is the solidus temperature, and here it is the corresponds to the liquidus temperature. So, it starts from the liquidus temperatures and comes to the solidus temperature, and that phase change happens with this range of the temperature, because it is an alloy system. So, binary alloy system, it is consists of the component A and B, and that in that way we can represent that different cooling curve if there is a change of the composition. So, here basically the pure 100% A composition, here at this point the 100% B. So, both the cases we can consider as a pure metal, but in between any stage this is the certain percentage of the A and certain percentage of the B, they constitute some alloy system, and that alloy system actually change the phase from solid phase to liquid phase to solid phase, and that actually happens over a range of the temperature. So, this is the time versus representation of the typical temperature versus time. But if we look into that temperature versus composition, here we can see that x axis actually represents the composition. So, here A at this point it is basically exactly 100% A, that means we can say it is a pure metal at point A. Similarly, at B 100% composition is 100% B, that means it is a pure metal B, but in between there is a mixture of A and B, certain percentage of A and certain percentage of B exists. So, at any point we can define this is the if you draw any vertical line. So, that actually represents the composition that consists of A plus B, and any proportionate way may be different at the different point. So, it starts from 100% A, gradually if you moves towards the x towards the positive direction, so towards the B, then here percentage of A actually decreasing, and gradually here the A is the 100%, and here at this point A is basically 0%. Similarly, if we move in other direction, B is 100% and here B is the 0%. So, in that way we try to represent the composition along the x axis of an alloy system. So, this alloy system, and if we at intermediate point at any point, its alloy system consists of A plus B. So, here the this point it starts the solidification and it's solidify, it's a completely becomes the completely solidified. So, in between there is a mixture of the solid phase and the liquid phase actually coexist, that the two different line. So, this line is basically represents the liquidus temperature line and this line curve basically represents the solidus temperature line. So, in this the simplified way we can represent the cooling curve of an alloy system. Now, we look in further analysis of that. Now, that basic understanding of the solidification in welding process. So, how it happens in case of the solidification process. So, in this case mainly the driving forces is in the solidification of the, we will just try to look into the solidification of the pure metal. So, here the driving force is mainly the undercooling or supercooling. We will come back to that analysis of the undercooling and the supercooling. So, in this case the solidification mainly happens in the two phase. First is the nucleation, and that means phase transformation may happens in these two phase, the nucleation and then subsequently growth. And nucleation basically involves that the formation of the small stable particles, that is called nuclei of the new phase from the liquid. So, if we look into that picture, so suppose this is the liquid metal. So, when this liquid metal exactly comes from superheat temperature to the liquidus temperature. So, then there is a start of the formation of the small nuclei, small particle, and that particle and the liquid metal actually coexist. And after certain, when it crosses the solidus temperature, then the consist of the all are the solid particles, but that afterwards the solid particles may also grow and it will try to consume the completely replaced by the liquid phase molten metal. So, in the growth stage basically the stable nuclear size is mainly increases as a result of the parent phase, and that gradually that parent phase basically liquid phase gradually disappears. So, initially partially disappear and gradually completely disappear. So, this is the simply phase change occurs with respect to temperature, and that also we can find out in the solidification process. Now, progress of the phase transformation. So, that means liquid phase to the solid phase transformation is consists of the two components. First is the nucleation and the growth process. So, nucleation process, there may be the two types of the nucleation process. One is the homogeneous nucleation, another is the heterogeneous nucleation, and both these cases there are some driving forces that actually promote the homogeneous nucleation or whether it is promoting the heterogeneous nucleation. So, we will try to find out what are the driving motive for these two types of the nucleation process that we generally observe in general the solidification process or in specific to the welding. So, homogeneous nucleation, it starts with the formation of the critically sized solid from the liquid. Now, the driving force for the homogeneous nucleation is basically the undercooling, high amount of the undercooling without any external interface. So, if we purely the basic elemental part of the homogeneous nucleation is simply driven by the presence of the undercooling, but how it happens the undercooling. So, if you look into this curve during the cooling process, it is this line indicates the actually the melting point, or that means that temperature actually decides the transformation from the solid phase to liquid phase or vice versa, liquid phase to solid phase. But during the cooling process, this before change of the phase, the material may subjected to locally let us say amount of the undercooling. So, that is the with respect to that melting point, this is the amount of the undercooling that represented by the delta T, that is the below the phase change temperature. Now, once this achieves some undercooling and it starts the nucleation process, and then after starting of the nucleation process and then it is exactly come back to the equilibrium temperature, that means the temperature that decides the phase change between the solid and liquid. So, reach the equilibrium temperature and then it change the phase, and finally, then evolution of the latent heat is basically starts after the undercooling of this system. So, then it starts this point, reach locally achieve some amount of the undercooling and then release the latent heat, and then finally it follow the cooling to the gradually, after changing of the phase, it gradually cool to the ambient temperature by releasing the specific heat in this case. So, this undercooling is the main driving forces, and that undercooling is specifically responsible for the homogeneous nucleation process. That nucleation actually happens throughout the structure at a time. But of course, this undercooling actually reach or achieved in a very local position within the pool of the molten pool, within the pool of the liquid metal, at which point there is a undercooling. Several point can be undercooling locally, some amount of achieving this undercooling, and that once it achieves the undercooling, then it starts the nucleation process. So, this type of nucleation process is mainly known as the homogeneous nucleation process. Of course, there is another nucleation process. So, in this homogeneous nucleation process, probably there is no role of the external surface. So, presence of external surface, that is maybe adjacent to the liquid metal or maybe some interface with the liquid metal, that actually also actually acts as a sites to create the nucleation process. But if we try to theoretically look into the homogeneous nucleation process, so here the driving force of the homogeneous nucleation process is only the undercooling. So, the degree of undercooling is more. So, tendency of probability of formation of the nucleation, homogeneous nucleation will be more. So, in this case homogeneous nucleation, the role of the external surface is no more there. Now, if you look into little bit about the theoretical aspects of this nucleation process, probably then it will be more beneficial to understand the solidification process in welding. So, we try to bring these two things. So far, we understand that solidification in a simple way. We understand that there is simply change of the phase from liquid phase to solid phase, that may happen one single point temperature, or that may happen over a range of the temperature, whether it is pure metal or whether it is some alloy system. Now, if we define the volume free energy, that is the free energy difference between the liquid and solid phases, because during the solidification process there is a change of the liquid to the solid phase. So, during this change of the phase, some amount of the volumetric energy is required to change from liquid to solid. So, that is can be defined as a volume free energy. But another surface energy, that is also energy needed to create a surface from the spherical particle. If we assume some spherical size of the nucleus as a sphere, so for the spherical particle, what is the amount of the surface energy is needed to create a surface, basically energy needed to create a surface. So, that means total free energy change in this process is consists of the two components. One is that over the volume over the surface. So, that is over the volume, the first component 4/3 pi r cube, that represents the volume of a spherical particle, and delta G V is the volume of free energy. Change of the free energy is required to change from solid to liquid phase, and that with per unit volume. So, that means volume free energy, this is the first component. Is the second component is the surface energy. So, 4 pi r square is the area of the surface for a sphere or spherical particle, and gamma is basically the specific surface energy of that particle. So, that delta G represents the total free energy change during the nucleation process probably. Now, this free energy change can be represented graphically, that if you look into the graph also, here you can see that one component, that this one, that actually representation of the volume free energy change during the this change of the phase from solid to liquid to solid phase. So, it is a negative we consider, but that because this actually represents by the difference the liquid and the solid amount of the energy needed, the difference between the liquid and the solid phases. So, it is a negative quantity, and other is the second component, that is the surface energy to create a surface of a spherical particle. So, this is growing positively, that means amount of change in this thing. Now, overall total free energy change can be represented like this. That means, initially total amount of the free energy is actually balancing between the surface energy and the volume energy. So, balancing these two, it is initially growing and it reaches some maximum point, and then again amount of the energy actually reduces, and finally it reaches to the negative value. Now, from this typical nature of the energy total energy free energy change during the nucleation process, we can find out that this optimum point is the amount of the optimum energy, that this amount of the optimum energy is the maximum amount of the energy is required to form a stable nucleus. So, that optimum point or the optimum energy level actually decides what may be the size of the nucleus, so that it can sustain, and that this critical energy simply estimated by the derivative, first derivative of free energy, total free energy change, making is 0, and then from this we can find out that size of the nucleus. In this case, the critical size is basically can be represented at in terms of the specific surface energy and the volume free energy. So, that R star equal to minus twice lambda by delta G phi. So, that it is a ratio of the surface energy by the volume free energy. So, that means these two types of the energy actually decides what may be the critical size of the nucleus, so that that nucleus can grow further. But what is the total maximum amount of the energy or optimum amount of the free energy change, that is also related to that the surface energy and the volume free energy in these cases. Now, critical size of the nucleus, it is a some negative sign is there, that means it is a depending on the what is the sign convention, what we can consider the is the delta G V. So, because of that time sign convention, that negative sign is there, but we can consider the magnitude of this size of the critical nucleus. It is a ratio of this 2 times of the ratio of this specific surface energy and the volume free energy, to change volume free energy related to change from the liquid to the free energy difference between the liquid to the solid phase. Now, this amount of the optimum amount of the energy or is also represented in terms of these two components, that volume free energy and the specific surface energy. But if we see that volume free energy can also be represented in term, also depends on the latent heat and the degree of undercooling, that means the temperature difference between the equilibrium solidification temperature. So, that means equilibrium solidification temperature maybe you can assume at is the phase change temperature, single point phase change temperature, and it is the latent amount of the latent heat. All this actually decides the decides the amount of the free energy difference between the liquid and the solid phase for a specific material. Therefore, delta T can also be represented by the temperature, the phase change temperature, and T is the temperature in between. For example, here it is can be represented the equivalent solidification temperature, and T can be any intermediate temperature T. So that the Tm minus T is basically represents the amount of the supercooling here. So, or L is the latent heat. So, this is the typical calculation of the size of the or amount of the energy required to start the nucleation process, or the stable nucleation process. What is the energy barrier probably required in case of the homogeneous nucleation process. These are the typical expression of the size of the nucleus, and what is the optimum amount of the free energy change is required to start the nucleation process of stable nucleation process.